In this video, we're going to go over the different parts of the data path, the units that are in there and how they work. And what we're going to start with is the ALU. So as we saw in the previous video, the ALU is the part that does the arithmetic, the arithmetic logic unit. It does addition, subtraction, multiplication, division, and logical operations. So we're going to see how that works. So we're going to go through one by one all of the operations that the ALU does and the gates used to carry that out. So the first two we're going to go over is and or, because that's pretty obvious. So we saw that the ALU has two inputs. So if we just have two inputs and we want to do and or, we can have an and gate and an or gate. And here's mux that we talked about. So this, we send in a control signal that's going to tell it whether we want and or. If this control signal is a 0, we'll get an and if it's a 1, we'll get an or. So this would be just a unit that does and or. So we also, besides and or, as we saw, we want to add. So we saw in the last module how to create an adder with two inputs, and actually three inputs that carry in. It'll add two inputs. So if there's multiple bits, we're going to have a carry in and a carry out, and the sum will come out. So here's just the unit and its carry out output. We haven't talked about the actual output from the adder yet. The carry out will be true if any two inputs are true. So if A and B are true, or carry in and one of the other two are true, then this will be, the carry out will be 1. So here's the add unit. We haven't had the output yet, but here's the carry in, the carry out, and the two signals. So here's our unit now that has and or and an adder. So we have two inputs and a carry in. So this is a a 1-bit result. So 2 bits get put in. And if it's 32 bits, there's going to be 32 of these units. And the operation, if it's 0, it's and. If it's 1, it's or. If it's 2, it is going to be add. So the result from the adder comes out here. The carry in goes here, and then carry out will go down to the next higher significant bit. So obviously now we have a 2 that can come into our mux now. So this control signal is going to be 2 bits so that we can have the 2 represented. Now we also want to do subtraction, but we can do that by just negating one of the inputs. So A minus B would be A plus the 2's complement of B. So take the reverse of B and add 1, and that would be A minus B. So we just take the complement, we just take the 2's complement or negate B, add it to A, and that would give us A minus B. So now we're saying if we want to do A minus B, so if we want subtraction, we would, if we want A minus B, we would invert this B and send a signal of 2 into here, and then negative B will come in, and A will come in. So to get A minus B, we turn this signal on and send a 2 in there. And we can do that with A. So if we want B minus A, we would set this to 1 and this to 0, and this to 2, and that would be b minus a. And we'll talk about what this is in a second. So as I talked about a second ago, this is an adder, but again, each of these adders here is for 1 bit. So if you have a 32-bit word that you want to add, or 32-bit number you want to add, you have to have one of these for each bit, and the carry out gets sent to the next higher significant bit. And I would say the carry end of bit 0 is going to be 0. So we also need to look at overflow detection. So if we add two numbers and the result can't fit in 32 bits, so that happens, or we can tell that there's overflow when the most significant bit and the carry out don't match. So if it's an unsigned number and the carry out is 1, we know that's overflow. There can't be a carry out on an unsigned number. But if we have arithmetic, the overflow is indicated when the most significant bit and the carry out don't match. So if the result is to be negative, the most significant bit should be 1. We learned that 2 modules ago. And if the result should be positive, the most significant bit should be 0. So if we're adding two numbers, we can't have the most significant bit be 1. So we'll know there's overflow. If we're subtracting a larger number, if we're saying a minus b, and we know b is bigger, and this is 0, we know we've had overflow. So here is our unit for overflow detection, and so that would just be in the highest order bit. So we would have this XOR gate. So if they're different, this would be 1, and that would indicate overflow. So we're talking about we're making a data path for a smaller set of instructions than really there is in MIPS. It's just our smaller set is just to kind of get a representative view of what the data path would look like. It would be too complicated if we had to support all of the instructions, but one we are talking about is set on less than. So here, set on less than, if A is less than B, so if the first register you send into your instruction so if T1 is less than T2, this will generate a 1. If not, it'll generate a 0. So we need some kind of signal that will tell us if A minus B is less than 0. So that's what that less signal was we saw a few slides ago. So that it's used on the least significant bit. The result will be 1. So if less is true, then the least significant bit will be set to 1. Otherwise, it'll be set to 0. And so that's the set bit. And that's only used, and again, the least significant bit. And then, but logic is only needed in the ALU in the most significant bit to generate set. So in the most significant bit, if if A minus B is less than 0, then the most significant bit will be 1. of the result when we subtract them. So then we send an output of 1 to the least significant bit. If that makes sense. We do the subtraction. If the most significant bit of the result is 1, we send 1, the output we send is not that actual subtraction, but just a 1 in the least significant bit, and that's for an SLT instruction. So here's our ALU again. So we have a signal of 3 if it's a set on less than. And then actually here is the ALU is a little more complicated for that most significant bit, because that's the one where we're going to see the overflow, and that's the one that's going to tell us to set the least significant bit if it's a less. So here, if the operation is 3, and this set becomes true, because it does subtraction, if it's less, if it's a 3, it's going to do subtraction, and this will tell it if A is less than B. So here's our whole ALU with our plus, minus, less. So here's set going back from the most significant bit to the least significant bit to set it to 1 if it is indeed A is less than B, and then the other inputs. So another one that we have in our set of instructions is a branch on equal. So here it's going to just say if, so we have the BEQ, then we have an offset, whatever we want our offset to be, so say 8 bytes. So if these two are equal, then we're going to branch. So all we want to know is if I subtract T2 from T1, is it 0? So all we need to do is check, we have to do an A minus B and check that all of the bits are equal to 0. So if everything is equal to 0, so this is not 31 or 30 or 29, 28. So if they're all 0, this is going to be true, because this is not that one or that one or that one or that one or that one and so on. So this is the 0 flag. So now we're going to put on the end of this our 0. This is our OR gate on the end and our indication of 0. So we're going to negate B, take A minus B. So now we have our ALU that can do branch on equal, set on less than, plus, minus, and an OR. And so now here's our ALU, so what we just drew in a teeny thing. So now, from here on out, basically we're going to see this as this triangle thing with 2 inputs. And the result, which will be the result of the operation for and, or, plus, and minus. It'll be a 1 if it's set on less than, and A is less than B. And then there's this also just this 0 output for branch on equal, just comes straight out of here. Is it 0 or not? So is branch on equal true? So is it equal is true? So now we have this 4-bit input here that's going to tell the ALU what to do. So this is saying I need a 4-bit control signal. So we had it up to 2, but with all the things the ALU has to do, it gets up to 4 bits. So when we were building it, when we had it up to 0, 1, 2, and 3, that was 2 bits. But there's actually even more that the ALU has to decide. So the control signal is 4 bits. That's going to tell this ALU what kind of operation it's supposed to do. And where it gets that information, it figures out what it has to do from the opcode. So we learned about opcodes, those highest, most significant 6 bits, and the function code. So we learned that if the opcode is all zeros, then it's R-type. There's going to be a function code, so that's bits 5 to 0, so the least significant 6 bits. So these two parts of the instruction are going to tell the ALU what it has to do. So here's those 4 bits again. There's a little control unit. This is called the ALU control unit. And so first it's going to take in the function code. So those are those lower 6 bits. And it's going to take another control signal that we'll go over called ALU op. That's a 2-bit signal. And it's going to generate 4 bits that'll go to the ALU that will tell it what to do. So we're going to look at all the things that ALU op can be. But if ALU op is 1, 0, then use the function code from the instruction. And we'll also look at the other values of ALU op and what they can be. So here are the 4 bits that the ALU control, or the 4 bits that go into the ALU to tell it what to do. So if those 4 bits are all zeros, then do an AND. If it's 1, do an OR. 1, 0, add, subtract, set on less, then a NOR. So this is also in your book. You'll find this in your book. So if I have an R type, like we just said, so if the opcode is 0, then use the function field to determine what operation to do. If it's a branch, we're going to subtract. So if it's a branch operation, we're going to send the subtract signal. If it's a load store, reminder, we have to use that ALU to calculate an address. So if it's a load store, we're going to tell the ALU to add. So if it's a load store, it's going to send a 1, 0. If it's a branch, it's going to send a 0, 1, 1, 0. If it's an R type, it's going to read the function field and decide which of these to do. So again, this is the same idea. If the opcode says it's a load word, so remember the opcode is bits, the most significant bits. So if the opcode in these bits says it's a load word, ALU op is going to be 0. Those are the 2 bits into the ALU control unit. And then what's going to come out and go to the ALU is 4 bits. So if it's load word, 0, 0 gets sent into this ALU control unit, and 0, 0, 1, 0 gets sent out. So this is the ALU control unit. Two bits in and the function code, and 4 bits out. So function code and this ALU op comes in, 4 bits go out. If it's load word, we don't care what the function field is. We only care about it if it's R type. 0, 0 comes in, 0, 0, 1, 0 goes out. So if it's a store word, again, it's the same signal because we want to tell it to add. So when 0, 0 comes in and 0, 0, 1, 0 goes out. If it's a branch on equal, we send in a 1 to tell it we don't care what the function code is, just send a subtract. If it's R-type, we're going to send in a 1, 0. That was a few slides ago. And that's telling it, look at this other input, which is that function code field. So then if that function, if your input is 1, 0 from ALU op, and this is the function code from the instruction, then it's an add, and so on. So here's from your book, the truth table for the input to the ALU control is the ALU op and the function field. And then the output is this operation, that 4-bit ALU control signal that goes into the ALU. So if it's 0, 0 coming in, we don't care about the function field and we do an add. There actually isn't a 1, 1, so that's why they put an X here. It's going to be 0, 1, but we really don't care about this one because this is the only one where this is a 1. Again, we don't care about the function field. We do subtract. If it's 1, 0, and again, since we don't have 1, 1, as long as there's 1 here, we know it's an R type. And we look at the function field from the instruction. And it looks like these are never used. So the difference between and, or, nor, add, and subtract is in the lower 4 bits. So here's some and or gates that carry out the operation. So again, this is 2 bits in, ALU op 1 and 0. The function field from the instruction, but only the bottom 4 bits matter. And you can have a look at that and prove to yourself that it works. And then the 4 bits come out. So the output from the ALU control unit is a 4-bit operation signal. So here's control signals and how derived from the instruction. So it looks like I lost a little bit of formatting when I went to explain everything, but this is an R-type instruction and a load instruction. So what happens when both of these go through the data path? So this is always the opcode. So it's going to read the opcode. First things data path's going to do is going to read that opcode to figure out what's going on. For both R-type and load, this is going to be a register that's going to be read, no matter what. For an R-type, this is also going to be read. For a load, this register is going to be written. So we're going to see some control signals about whether this is something to be read or something to be written. And then this, for a load, is that register is going to be written because that's where the result's going to go. So we're going to write a register for both of these, but somehow we have to give it the control signal to indicate which register, which bits indicate the register to be written. Is it bits 11 to 15 or bits 16 to 20? So that's more of the control signals we're going to look at. Is 1, do I have to write a register? And 2, which bits tell me to get the number of the register to be written? So we're going to go through some of these examples. And then we're also going to see what happens when it's a load. We're going to have an address here that needs to be sign extended and added to. So we're going to see how we handle that. So we're going to see a sign extend unit, and this could be sent into the ALU, this value. And then here's 2 more. So on a store, this is the opcode again. We're going to read this register like we always do. And then we're also going to read this one. And then this is going to be the address that we're going to sign extend. On a branch, this is the opcode again. We're going to read this register and we're going to read that register, and this is the offset, so we're actually going to take this, sign extend it, and then we're going to shift it left too, and add it to the current address. So we'll see how that works. So here's our data path with our control unit. So we talked about this little ALU control. Don't get that mixed up. This is the big control unit. So these are all the signals it's going to send. So this one here is going to say, which one of these two registers do I write to? If I'm doing a load, I'm going to write to this register in this part of the instruction. But if I'm doing an R type, I'm going to write to this one in that part of the instruction. So remember, we saw the different fields. So this is that field in bits 11 to 15 for an R type is the register that I'm going to write to. And then here for a load, this is the register I'm going to write to. If I'm doing a branch, I have to send this control signal. This is telling me it's a branch on equal. If I'm reading from memory, that's if I'm if I'm doing a load word, I'm reading from memory. If I'm sending a value from memory to a register, that's a store word. I'm going to send a 1 to here to tell it it's a store word. This ALU op we already learned about, so I'm looking at what kind of instruction is this. Remember, and we had the 1, 0 if it's an R type, 0, 0 if it's a load or store, and so on. So that's where that value comes from. So it's taking the whole instruction into here. It's actually just taking the opcode and coming up with all these signals. So memWrite, if I'm a store word, if I'm store word, I'm going to write something to memory. ALU source, am I a load? Or if I'm a load word or store word, this bottom input, the sign extend, I'm calculating an address, so I'm going to send a 1 to say this is the bottom input to the ALU. If I'm R type, I'm going to say, oh, use that second register. So that's ALU source. Register write, if I'm either an R type or a load word, I'm going to send a 1 and say, yep, we're going to be writing to a register. So that's how we just take the opcode and come up with all these signals to tell it what to do. So here's for R type. This is what gets used. This just like kind of brightens up, like it grayed out all the parts that don't get used. So on an R type, I'm going to get the program counter. I am going to add 4 to the program counter. I don't care about this, so I'm going to send a 0. And so all I know is if I do an R type up here, this part I'm just adding 4, and so I know I'm going to just get the next instruction. Then down here, I come in and I say, all right, so for an R type, I have to send in 2 read registers, and then this third register is going to be the one I write to. I'm going to, this is the value that's going to go through and get sent to the bottom input of the ALU. It's going to be from a register. I use the control unit and tell it what I'm going to do with it. And I don't care about memory, the data memory, because it's not a load or a store. I come around to the mux, and so this is saying we're going to write a register that's mem to reg. So all this is telling us is that we're not writing from the memory, we're just taking this value that came out of the ALU and sending it back into the registers. And then now load. Similar, I'm just going to add 4, so up here is just getting the next address for the next instruction. I'm going to send in the 1 register, and then the second one This register here is going to be the one I write to. It's a load word. And I'm going to send the bottom 16 bits into this sign extend unit. And then it's going to go up here and be the bottom input to the ALU. I'm going to write that. And this result from the ALU is going to tell me what address to read. So I read the data, get the data out, and send it back and put it in a register. Branch on equal. Here I'm actually going to say, all right, so up here I'm going to add 4, but I'm also going to get the result of my operation to figure out what the next instruction is. So I get that by reading the 2 registers. So the result, the inputs to the ALU is going to be the 2 register values. It's going to go in, and the ALU is going to tell it to subtract. It's going to subtract, and then this 0 will come out. If it's 0, and this is true, and this is saying it's a branch, so it's a branch instruction, and if this is 0, it's going to send this up here. What it's going to do is use the input from this little adder up here, which is adding together the bottom 16 bits of the instruction, sign extended, shifting left 2 multiplies it by 4, because remember this is a number of words offset, but our instructions are in bytes, so we have to multiply it by 4 to get the correct number of bytes of our offset. We add that to the current PC plus 4, add the shift left 2 value, and that's the result, and that's going to be our new address of our next instruction. And jump. So all that does is calculate a new address for the next instruction or program counter. So all we have to do is, if you see that it's an opcode for a jump, which is 2 in the upper 6 bits, all we have to do is take this address, multiply by 4, so do the shift left 2, and go there. So here's our jump instruction. So here, if it's a jump, we're just going to send the lower 26 bits through here, multiply them by 4, add it to the current program counter, and that's just going to be our next. We have a second mux here that's saying if it's a jump, this second mux will have a value of 1. And so that's all this one has to do. It doesn't need any other parts of the data path. So this instruction subset has these signals that we just went over. So these are our control signals for our instruction subset. And then we don't have the jump one in there. So we had the jump in the one slide, but now we didn't include the jump. Or there's that other control signal we had for the jump. The one. I don't know why I included those slides and didn't include it in this table. Oh well. Anyway, so here is inputs are the opcode. So this is the 6 bits of the opcode, which is 31 to 26. And then what the output control signals would be for each of those. So if it's an ARP format, I'm saying, okay, so use that third register. We're going to write a register and send 10 as ALU op. If it's a load word, we're saying use that bottom value as ALU source. We're going to write, go from memory to a register. We're writing a register again. We're reading from memory. If it's a store word, again, that bottom input, and we're going to write to memory. If it's a branch on equal, it's a branch. send 0, 1 in as ALU op. And this is what our inputs and outputs look like. So this would be the AND gate, determine that it's R format, and then each of these, if you go over here, this would be a 1. So if it's R format, we're going to have a 1 for register DST and ALU op 1 and register write, and so on. So that's just carrying out that table in the last slide. Okay, so this was our single cycle option. And so the longest instruction, so it's set up so that in one go through the whole thing, no matter what kind of instruction it is, that whole data path will be in use. So whichever instruction takes the longest will be the clock period. And it's actually the load, because that one has to go through the register file, the ALU, the memory, and then write back. So the clock period is going to be determined by how long the load word takes. So we're going to look at multi-cycle versions in the next 2 weeks.